Okay, so we are actively recording. I am. You all got the syllabus, right? Same old, same old. By this time, you've all done syllabi forever. So it's the usual. It's exam based for exams. None of them will be cumulative. Study guide, objective format. But when we do lab, it'll be different. Because lab is going to be presentation based for grading, and lab will be activity based. So we'll talk about the lab and the lab. The most important thing I was able to get, thanks to Dr. Badger, from a lab perspective, was to get us out of the lab with those horrible wooden stools. So we 141. I mean, it's not padded. I'd rather have the environmental science lab, but hey, you do the best you can. Dr. Lasota's in there between 3 and 4. So if we really felt uncomfortable, I suppose we could switch if they haven't taken it up. But so we're down right below in 141, and we'll go from there. So because it's going to be that tech-based stuff, and I'll go over it and I'll demo the tech, and you'll see what it is, and we have effectively unlimited downloads and things, and I'll talk all about the lab stuff. So we have a couple of wet labs, and mostly tech labs, and unfortunately, there is, unlike anatomy where I run out of stuff and have to find stuff to do. I have no problem with that in physiology. All I have to do is keep talking. So is immunology running this go round or no?
That'll be next year.
That'll be next year. Okay, so that means I have to do extra on the immune system. So usually there's immunology. I don't not do it. I just don't do it as extensively so I have to sort of hybrid the intricacy of it. So that's everything. I'm recording now, as we always do, and we'll send it, and goodbye. So I'm not effectively this. Let me show you Blackboard wise. Basically it's the same Blackboard show we had for anatomy for those all but one with the anatomy. I guess Malachi is studying abroad. I think that's I read that. Yeah, that's great. So all the old PowerPoints are probably still on 1, 2, 3, and 4. So effectively, our week 1 is week 5, our week 2 is week 6, and again, that corresponds to the exam. So our first exam content is for week 5, our second week 6, 7, and depending on how I always hybrid it a little differently. Not for the first exam, which is going to be substantially review of cell with my spin on it, and a lot on muscle phys, and at least starting, if not completing, nerve phys. Everybody, muscle and nerve phys is hard. That's a hard part. Hard parts on this are muscle and nerve phys. The third exam is immune. I think that's where the immune content is. I think muscle phys, nerve phys, a little cardiovascular, though a lot of times I do that in lab, and immunology are the hardest portions of this. Endocrine maybe is important to a lesser extent. I always get it. Repro has some certain complexities, and I do a growth and development, and pardon the expression, aging. Thanks. One person smiles. Emma's the only one who smiles. It's okay. 72 and a half reasons why I'm not happy with that.
Really depressing.
What?
That was really depressing.
Tell me about it.
All right.
I don't even like me it's so darn cold out. It's not pleasant to go out there.
I know. I'm surprised you didn't cancel class.
In what?
I'm surprised you didn't cancel class.
Oh, no, heavens no. Tempting, but no.
Oh, you never canceled class.
No, I don't like to cancel class too much. No. Goodbye. All right, so here we are.
Goodbye.
Goodbye. So I've reloaded this so many times, it keeps showing up again. So I probably double loaded it, and I don't care. And so basically our chapters from the text are parts of 3, parts of 9. 9 is the muscle phys, and 11 is the nervous phys. There's a tremendous amount of content, which means we start. So on with the show. So, you probably you've seen this chapter in 100 textbooks, all about the cell and cell theory and all the different kinds of cells, and I don't care. Okay, what parts that I think are significant, the thing that, and I like to look at the core concepts of physiology. Number one on the hit parade, you've all done it, movement across membranes. Diffusion, osmosis, facilitated diffusion, active transport. That's the first thing we do with this. What we'll get into is perhaps some today, certainly quite a bit on Friday, is going to be resting membrane potential. Everything hinges on these. The movement across membranes sets resting membrane potential. And resting membrane potential for most cells is constant, except for the cells that do stuff. And the cells that do stuff, like nerve and muscle cells, rely on sudden dramatic changes in resting membrane potential. And all of that is compensated for by movement across membranes, whether it's passive or it typically develops from passive and then becomes active. And so you're going to get a chapter and verse on leaking channels, voltage gated channels, ligand gated channels, et cetera, et cetera. And how much of that you do with Dr. Helwig, I don't know, but probably a fair amount, I would venture to say. Okay, so I'm not going to sit there and go over this is the cell and this is the nucleus and all of that, and the ICF, VCF, and the fluid mosaic model, and don't. It's when we get to here, the membrane. And it's not so much what makes a membrane, it's understanding the membrane and its roles, because this is where that all shakes down. Whether something can pass through the membrane easily, read that as small, fat soluble, and non-polar, versus anything else, save water, which is small. So effectively, the only really polar particle, unless there are channels provided, is water, because of its size, and most of our cells are water permeable. Not all, okay, but mostly water permeable. And the other side of that is then we start talking about the channels, and particularly those leak channels have a lot to do with sodium and potassium. And then we get to the whole thing of the resting membrane potential. So it's about not just the phospholipid bilayer with embedded proteins, et cetera, and lipid rafts and all that good stuff. It's about everything else that goes on. So specialized proteins floating around, the old fluid mosaic molecule. The really important aspect of the projection of the sugars, glycocalyx, sugar shell, is how that means. And what protrudes from that are the identifiers. Everything that we have that really makes our cell identifies it specifically to our immune system and for cellular interactions is that sugar cell. And again, we do a lot about that. And I think the way I have it scheduled this term is circa around the break, is we do our blood lab. And I'll give you, again, my spin and my understanding of blood compatibilities and ABO and all of that stuff. And unfortunately for me, in the past, I have a lot of information to share with you about that. Because I've had, I don't know, somewhere between 50 and 75 units of other people's blood in me in about a year and a half span between 1998 and 2000. That's when I got funny. You see, I was very dull and unpleasant and not creative. And then I obviously got funny blood from somebody. You're not really receptive today, are you?
I'm sorry.
Yeah.
It's very cold outside. I'm just saying.
There's a great song about that. Baby, it's cold outside.
You're gonna have to sing the entire song.
No, I will look at the late Tony Bennett and Lady Gaga. Did a pretty good version of that. What?
It'd be more fun if you sang it.
Not with my voice. My wife doesn't. She does not like my voice.
Oh, that's me.
She's like, "Don't sing." Okay. So, and cell junctions, we know about desmosomes and and we'll go over that every so often. So here we have a potpourri of a variety of different integral proteins and membrane proteins and transmembrane proteins. So here's the structure and hydrophilic and hydrophobic, and we're not going to go crazy with that. But this is the big part. There's 6 subcategories, at least to be familiar with. And I'm sure you've had these, so a lot of it is review. Cell-to-cell communication. Most of the time, that has to do with particles that are being excreted and trigger or receive, depending on the kinds of particles they are. The large amount of the mass of the plasma membrane certainly is from the membrane protein and all of their functions, and it depends whether they're integral, incorporated in the membrane, or peripheral proteins. So the integral ones, and again, the beauty of it, you did this in biochem and you did it in cell molecular. The interesting thing about how proteins fold in their tertiary configuration is the fat soluble, the hydrophobic portion seems to be centrally placed, and the hydrophilic, okay, the water soluble portion projects both inside and outside. So they're able to embed themselves by the nature of the way they fold. All those wonderful van der Waals forces, stuff that you all learned about already. So the hydrophobic areas interact with lipid tails, hydrophilic interact with the water-based aspects of it. And so, and they have a variety of roles, and they go through all of them. The peripheral ones, technically speaking, are attachments to the hydrophilic aspects, and whether they're filamentous or not really doesn't matter. It's their functionality to me, because that's what the course is, physiology. Enzymes, motor proteins for shape, interconnectors, etc. And so they go, and it's a bad slide because you can't really see it. But when they do it this way, you can see it. Transport. And so basically it's always different categories. You can have ones that are more like channels, and by channels, by definition, are always open, as opposed to ones that change shape, which we would classify as carrier proteins. And the channel proteins can be, as you will see, for charged particles or for water itself, being effectively pores with passageways. And you might describe them as leakage channels, particularly for sodium and potassium, versus ones that change shape, either without the input of energy, facilitated diffusion. When a particle comes in contact, it changes shape and allows the particle to come in or go out, depending on which direction you're looking at. And those where energy is imparted to it, and then you have, quote, active transport. To my way of thinking, what we try to do, active transport is just that. It requires energy. So you try to conserve energy wherever you can. And a lot of times, as you, and undoubtedly you know, what will create active transport to create concentration gradients like the proton motive force, so that you can basically, by actively transporting, now you can effectively create via active transport a non-energy requiring force to come back in. It's a good thing. That whole, chemiosmotic theory thing, Nobel Prize winning, all that good stuff, works for me. And you can do the animations if you want. I don't get a lot out of it. Receptors. Most of our chemical messengers, with the exception of those that are cholesterol-based, fatty molecules, and thyroid hormone, okay, because of its symmetry. And those can pass through the membrane because of their size and their absence of polarity. Everything else, indirectly, it functions on the outside and creates changes on the inside. That's the classic transduction that occurs. Somebody knocks on the door, all of a sudden we look. We hear an alarm from outside. Something happens outside of our environment, it changes something on the inside of environment. Okay? Any one of a number of examples. They're by definition very specific, and the changes can be either very specific or broad-based. So insulin, very specific receptor, changes on the interior side, massive. because it sets off a chain reaction by way of something you probably were already acquainted with called tyrosine kinase. So a lot about that. And I like to do a big size unit on diabetes because if you're going into any field medically, and you're going to know somebody with diabetes, you just are. So all of those, and there's different kinds of change. It can be shape changes. It can be different kinds of alterations. Those are receptors. Enzymes. Where you see this the most, by far, is in the digestive area, particularly small intestine. They're called brush border enzymes. So they're protruding from cells, and the proteins that are adherent are effectively enzymatic. And it's the way they'll do the final breakdown of particles to their smallest size so we can absorb them in the small intestine, like dipeptides and tripeptides becoming amino acids. Going from disaccharides, which we can't absorb, to monosaccharides. And the classic example is lactose intolerance. So lactase is one of those brush border enzymes. And we do this all over again with the specifics in digestive, okay, that are there. That's such a funny one because some people start lactose intolerance and it goes away, more so than others. Most people are born lactose intolerant, and then as it develops, it goes away. And some people develop it later in life. It's almost like it expires. And it's just phenomenal. I have two stepsons who became pretty significantly lactose intolerant. And it's to the point where it's just like, oh my God, if they get anything dairy, it's big trouble. I mean, I think it probably started when they were in their late 20s to early 30s. I mean, the youngest of these is, I know, 32. Don't start. Yes, sir.
How come some people still have that enzyme when they're older?
With having the enzyme?
Like the enzyme for lactose intolerance?
Oh, I don't have an answer to that. Some people are just very, very brittle for whatever reason. Maybe it's a genetic defect. Maybe it's a familial trait. I don't know. I don't have the luxury of my wife and I can eat anything, and it's not a problem. My kids, again, were all adopted, so I can't account for it. But her kids are biological, and like I said, the two of them, and where she doesn't have the problem, and as far as I know, her ex doesn't have the problem. So I don't really have an answer with regard to.
It's like designated to some ethnicities, right?
Yeah, more frequent. Yeah, I think you look at frequency curves that are like that. I mean, I like the fact that I can eat. We're pretty dairy oriented, which is a good thing. It's not, because I mean, it's not easy being cheesy. So much cheese, so little time. I love dairy. Oh, sorry. And without that, you couldn't have butter. And
The pill that people take to like eat dairy.
yeah, like the lactate.
It's those enzymes.
Yes, exactly. We used to do that with my middle one, who had the severity of it. We would add that, and then you could buy the milk with it. I mean, nowadays, you would use almond milk and things like that. That facilitated. I mean, he did all right with that stuff, but not perfect with it. Now he's pretty good with that stuff. Moving on. This is what I was telling you before. Short chain carbohydrates, cell to cell recognition. Proteins and the sugars that attach make glycoproteins. That's every single cell that you have, every single cell that you don't have, whether it's a bacterial cell, have glycoproteins, and therein, and when we do the immune system, that's the recognition. When we do blood groups, that's the recognition. And they're very, very similar, but they're not identical. In your immune system, it can be the subtlest of changes. If it's like this, and all of a sudden that knuckle sticks up just a smidge, all of a sudden you can have a vigorous and vicious immunological reaction. So be understanding of that, please. Attachment. Our cells are all attached. Very, very few cells biologically go around on their own. Okay, they're either like lining cells, and we talked about this in anatomy, Epithelial cells are basically sheets of cells, layers of cells that line. Connective tissue is just that. They're farther apart, but they're connected by a variety of fibers, which are part of this extracellular matrix. Short of white blood cells, and maybe to a lesser extent red blood cells, there aren't a whole lot of cells that are on their own. And those cells typically are red blood cells is an oddball in that regard. But white blood cells are clearly more along the lines of independent functioners, but they function in large groups of them, even though they're not necessarily tethered together. But and so that's the impact where when you distort a tissue, and we saw this a lot surgically, when you pull and tug on something here, you can create damage here because everything is interconnected. I can tell you how many patients that we encountered when we did an operation here, wonder why they were black and blue here. Well, you weren't supposed to work over there. It's all connected. Okay, so understand that that's part of it. And then the joining, and really there's only three major categories to review. The strongest one, desmosomes, which are like rivets. If you want to use that analogy, very, very strong construction materials. Tight junctions, and to me, tight junctions means watertight. They're surrounded, it limits the number of pores or openings potentially, and particularly in between the cellular flow of water. And then lastly, the gap junctions or connexons, which are protein passageways that allow signaling particles in different chemicals. Bone has them, for instance. The nervous system is filled with them. That type of thing. So here we are with, and the sugars are attached to not just proteins, but lipids, the classic cell-to-cell recognition, immune. When we do immune system, we go through about a 6-month period we call self versus non-self, where your body kind of becomes acquainted with who you are. It's the reason why sperm cells, if they get into the bloodstream, would be attacked because they don't form until puberty. So your body there's no genetic reference point with regard to that. It's just for instance in all of those things. So, and this is an injury, and I dedicate a lot of what I talk about, particularly when you get to the cell cycle, to irregularities that lead to cancer. All you have to do is, if you see, it's always astonishing when you see people who live very long and people who don't, and succumb to unusual cancers and terrible die. So I do dedicate a fair amount of time to talk about that. But here's an interesting note. That warning system, cancer cell would have an unrecognizable glycocalyx. Your immune system forms killer T cells, cytotoxic T cells, to that array, to that configuration. But it changes the configuration. So all of a sudden, the cell it's supposed to attack now is a different marker. And the cells don't see the cancer. It's just a series of rolling over things. And when they roll over something they're supposed to adhere to, they adhere to it. That's all it is. It just doesn't target the area magically. You give a systemic drug or systemic radiation and hope it does what it's supposed to do. So the mutated cell, now your immune system does not attack. Here you can see the different junctions, tight, and it's almost like bound together. The desmosomes, we're not going into the anatomy of it, rivets and plaques and things like that. And they unfortunately can be destroyed into connexons or gap junctions, simple signaling small molecules that are there. We'll see a fair amount of this when we look at the physiological mechanics of both cardiac and smooth muscle. Really significant because they're all networked together. Skeletal muscle is a little bit different in that regard because the signaling system is pretty well understood. They're both, to be fair, really well understood that are there. And now we get into the whole. Now I used to do, when I do AP1, there's so many creative ways to talk about, active and passive transport and diffusion and osmosis. But you guys have had most of this. And typically in the Bio 1 labs, don't you do simple exercise with osmosis or potatoes as osmometers? Love that. No? Oh, so if you ever worked in the fast food industry, what do they do with potatoes? So McDonald's takes raw potatoes, puts them through a specialized thing to make those they're really good fries. I like to consider myself a French fry aficionado. The difference between French fries and home fries are previously cooked potatoes that you fry up versus French fries, which are not previously cooked. What do they do with all those potatoes once they effectively put them through that slicing device? They stick them in water because osmotically it'll absorb the water and it'll make them firm. And then they're twice cooked. You do one bath roughly at 310 degrees Fahrenheit for X amount of time. It's a long timer. And that cooks them through. And then your second one is the exterior to get them that nice brown crunchy. Three cooking. But that's the idea of movement across membranes. So that's osmosis 101. Higher concentration of water to a lower concentration of water. So they put them in a water bath, which is, it would be different if you put it in salted water. Okay. And a lot of times you'll do things like that when you're cooking. It's like when you make pasta. You should salt the water because it's the only time you can season the pasta. I don't know where you get your pasta. Where I get my pasta, it doesn't come seasoned. That's not me. That's Emerald. The great sage of Emerald.
Can you just season the sauce?
You cook it in the sauce and it'll suck up the sauce, but within the pasta itself, a little bit different. It's okay. I'm having a pasta moment. I had mac and cheese for lunch. It was very good. You're fine. Okay. So passive, simple diffusion, higher concentration or lower concentration, pure simple diffusion. Well, you guys are always in the same seats more or less anyway. But you're kind of spread out, simple diffusion. It's not like you're all over there or all over here. In the movie theater, the whole deal, where you go find places, you sit where there's openings. And that applies, and there's no energy. It's just molecular activity, particles colliding with one another. The more they collide, the more they get pushed apart. It's a good thing. Okay, and any one of you, the old drop of ink in the water, see how it is. Okay, facilitated diffusion means you have to have some kind of either channel or carrier to facilitate. You have to have an opening that's there, one of those proteins, those transmembrane proteins. Whether they change, if they change shape, it's facilitated because effectively they're coded for a particular particle and or particles, typically one. And then osmosis, basically you flip this, it's the upside down approach. You all know it, and it's really important biologically because our plasma, our interstitial fluid, our extracellular fluid is all osmotically equal, and we get it, and really we're building to get into kidney. So roughly we have like 300, like our typical isotonic is 300 milliosmoles. I think most of you would be familiar with it. And it counts up not just salts, but salts, sugars, acids, hormones, solubility of proteins. All the stuff that's dissolved in the water exerts an osmotic impact. And it's, if you're going anywhere near a medical field, it's as important as any concept. Because when you give fluids to somebody, you've got to be very cognizant of whether or not you're going to overhydrate or underhydrate. Are you going to push too much fluid in, or are you going to suck too much fluid out? So we use isotonic media. And it's based on, fancy word, the colligative properties of water. So, I mean, what's in your plasma or my plasma, to a certain extent, is known. The actual concentrations of each probably varies a little bit. But the thing that your plasma and my plasma, assuming it's isotonic in nature, it has the same colligative properties. Read that as freezing point, for instance. So your plasma, if they extracted it in mine, should roughly freeze at the exact same temperature. And that's one of those properties. It's like In the old days, when you made ice cream with the old ice cream things like that, and you create like slush ice, you take rock salt and ice, and effectively it would lower the temperature of the ice. So it would create an environment. Maybe you did like camp ice cream and stuff like that. Just say. Mint chip moose tracks. Oh, oh.
I have a question.
If it's about mint chip moose tracks, I'm here to answer it.
It's the next best thing. It's facilitated diffusion. Can you like explain a little bit more?
Yeah.
Like when you exchange like two sodium for potassium.
Yeah, but typically you're using two channels. You'll have a channel that will bring in the sodium, and a channel that will, or the other way around, will extrude the potassium. Typically, it's the other way around. But the channels are specifically configured for the most part for one, and sometimes sodium and potassium channels will have two. You'll see that a bit when we start looking at neuromuscular junction. So facilitated just means you have something to help it or facilitate or permit it, and it means a protein carrier with the implication that it changes shape or changes, it opens or closes with the proximity of a particular particle. So here comes the sodium in the channel. When it gets close, it will open. And it's allowed to go into the cell, or potassium allowed to go out of it. And you'll see there's some very good animation with this particular textbook series that I like to explain that. And osmosis, effectively, the cells are always permeable to water. Water's so tiny anyway that, again, it's based on the concentration. So if you look, and you've all seen this more or less, basically, you look at two vessels, one with a couple of particles and one with, let's say, just with a bunch of particles, and let's assume they're the same size. So maybe you have 6 particles to 1 unit, and here maybe you have 20 particles to 1 unit. Well, so 6 to 1 particles to volume, 20 to 1 particles to volume, assuming the volume is made up of water. You flip it. So this becomes 1 to 6, and this becomes 1 to 20. And so that's the concentration of water, if you want to think of it that way. So, if you make the denominator, you change, here you have a lot more water, the water will flow in that direction. And effectively, we utilize that a lot to make sure that water, when cells have, for whatever reason, lost water, they'll pick it up, or if they have too much water, they'll push it out. So the main isotonic, rebalanced. And so that's when you infuse, like intravenously. The most common intravenous certainly wouldn't be plain water, is typically normal saline. And 1 normal saline means roughly 0.09, 0.085 typically, of sodium chloride, which when it dissolves makes 2 particles. And then you do the molecular weight, and you can figure out what the number, which you don't have to do. That's chemistry. We're not doing it. Or D5W, dextrose 5% in water, same deal. Figure out the molecular weight of dextrose, makes 1 particle, blah, 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 blah. In biological systems, we always use percentages. When you're in chemistry with whoever you did Chem 1 or Chem 2 or Dr. Badger, I'm guessing, when you had, you use you had 5 molar and all that kind of good stuff. 1 molar, these hydrochloric acid. Not anymore. Okay. But here we use percents. So I just had my blood test run. My blood sugar was, let's say, 90. So that's 95 milligrams percent, which means 95 milligrams per 100 milliliters of blood. That's blood sugar. So in biology, as you know, we use percents, and in chemistry, we use molarity and molality, depending on whether you're using concentration or weight. Right? I get that right? See, I'm not so thinking as dumb I am. I'm having such a good time. It's good to be back. Yeah, high movements, kinetic energy, there's the ink drop thing. How concentrated, and don't make no mistake, concentration drives the bus. It's all about the concentration. Size certainly plays a role. Small is faster. Okay, and temperature. Because what's temperature? Average kinetic energy. When you raise the temperature, molecules are just colliding with one another. And people have a mistaken idea of equilibrium. Equilibrium is no net movement. It's well expressed there. It's not no movement. It's not like all of a sudden everything stopped moving. It just means you're going to have a little bit of salt going in, a little bit of sugar going out, or the other way around. So if you happen to brine your turkey for Thanksgiving, you make a flavorful liquid, you immerse it in it, and eventually you get effectively brining creates a certain amount of moisture and flavor that's being absorbed. Turkey briners, help me. I have a great marinade for chicken that basically works on that. I have some. It's Asian. Okay, soy, a little bit of dry sherry, which is the same as rice wine, Shaoxing rice wine, and rice vinegar, a little bit of sesame oil, a little bit of hot sauce, whatever your choice is. I prefer sriracha, and a little bit of ginger, a little bit of garlic, a little bit of onion, a little bit of cilantro. Happy days. Put that bad boy in there. Put the chicken in there. Let it get happy in the fridge for a couple of days. Happy days. So, natural drive, differentially permeable, some stuff can get through. Diffusion, lipid soluble, non-polar, blah, 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 blah. So it doesn't matter. Diffusion can occur whether it's fat soluble or water soluble, is what they're saying. Here's the facilitated, because it requires the assistance of a carrier to really answer your question. And osmosis, we're explaining water, but you have to have channels. This is a big nugget. We talked about it a little bit when we did skin and anatomy. The two big things, your skin is a barrier. When that barrier is compromised, whether it's a partial or a full thickness burn, one, tissue that easily gets infected because it's denatured proteins and they easily get infected, and two, loss of fluid and electrolytes, much more significant with people who inherently have trouble with that and read that as very young and very old. That's who always is at the greatest risk with regard to that. It's like babies are vomiting and diarrhea and your Pedialyte or whatever they use today, all of that stuff. That's the whole idea. The Gatorade was invented as an electrolytically balanced substance, and it came out because it was named, you probably know this, University of Florida, the Gators. And when I matriculated, I know, here we go again. In college, my roommate was halfback on the football team, his freshman. And I said, "What do you eat at the training table?" He goes, "This, that." He said, "All the Gatorade we can drink." And that's back in fall of '69. I know. None of you were there.
Where?
Huh?
What's the question?
Well, you weren't around in fall of '69.
Just missed it by a few years.
Yeah, like 40. It's all right. My granddaughter, my eldest, was 22 on the 3rd of December. And so we went to say goodbye to my son, and she's ordering a cocktail. I'm like, spare me. Because she gets her ID right out.
You didn't tell me happy birthday.
I beg your pardon? When was it?
December 29th.
Oh, I'm so sorry.
It's okay.
Belated happy birthday. My wife's was January 9th.
Thank you.
I will tell her.
Mine's just New Year's.
What?
Mine's just New Year's.
Oh, happy birthday to you.
Anyone else have a birthday? Did we miss one?
How about an unbirthday? A very merry unbirthday to you, to me, to you.
Today's
No.
my dog's birthday.
Wow.
All right.
That's how you like that happy birthday.
My best friend's birthday was. Oh, there we go. Another.
Like that. No, so hey, when do you guys graduate? Oh, next year. Graduation is May 10th, which is my birthday is May 10th.
Yeah, I think it's. Yeah.
Yeah, I know. The graduation is the 10th.
Birthday. Are your birthdays the 10th?
Yeah.
You're like the fourth person I know with that birthday.
It's common. Fred Astaire is probably the most famous of the people with that birthday.
I don't know who that is.
Fred Astaire was great movies when ballroom dancing, long before Dancing with the Stars in the 30s. Fred Astaire was just this brilliant dancer who danced with Ginger Rogers, and the movies they made were legendary. Just saying. The book I'm reading now, for a little bit of trivia, is about, what was I going to say? Has to do with the relationship, sort of the love and sometimes the hate relationship between Olivia de Havilland and Errol Flynn in the 30s and early 40s. Swashbucklers like Captain Blood, Adventures of Robin Hood, Charge of the Light Brigade. Oh, it's so much fun because all the studio stuff that went on. Nothing new about that. She lived to be 104 years old.
Really?
She was born in 1916. My dad was born in 1914 and died 2020. And her sister was a couple years younger, lived around 100 years. And Flynn, who was a notorious drank and a terrible womanizer, not necessarily a great person, though, a strikingly interesting character. Only lived to be, I don't even know if he made 50. So moving on. Remind me to show you tomorrow. Anybody into cars? All right. Hey, no car people? What fun are you?
Ben likes cars. Ben loves cars.
There's a car show. You know, there's a car show at the convention center this weekend. If you're there, to divert a little bit, let me show you. It's because I don't give as much space to this kid as the others. Okay? He got that car. This is a Mazda that he got that basically had almost nothing functional in the store. And with the sport, it was like some ridiculous amount of horsepower.
Is that a Miata?
Yeah, it's like an RX-7 or an RX-8, something like that.
Those are pretty small cars.
What?
Those are pretty small cars.
They are not big cars. I think it's an RX-8. Yeah, and if you're interested, I think he's putting the price tag at 30. But send me the question, I'll send it to him. So he sent pictures to whoever the people were and entered, and they said, yeah, come on in and show it. So his buddy has a foreign car dealership in Oakmont, and they towed it over this afternoon after he worked. So, and my daughter nearly got snowed in Buffalo right before the game because her fiance was the college roommate here of the women's coach, the hockey coach. And he coaches an elite traveling junior type team. An illustrious graduate here of RMU, as I've said before. Just saying, just so you know, I haven't forgotten any of this stuff. Moving on. So, and they go through all of this stuff that you see before, and you can look at these examples, whether it's carriers or channels. The difference being the channels are always open, the carriers are not. And I'm starting to set the backstory. Carriers, transmembrane, very specific. They can be overwhelmed or saturated. That's another thing to remember. And again, they just change shape in proximity of whether it's changing shape to bring it in or to take it out. Channels, typically by implication, are usually open. And when they are leakage channels, they're always open. And then we're going to talk a lot. So remember the terminology about ligand gated, which means a chemical has to open the way, like insulin, directly or indirectly, and electrical signals or voltage gated. And that is so important about physiology of reactions to neural and endocrine stimuli. And we'll review a little bit about G protein pathways, and that. What I'm trying to do is give you an idea of how you use it, and whatever you all are going to do in the future. Whether it's just knowledge that you have for whatever your field is, or if you're in a medical or scientific field. And I think it's advantageous. Here you can see the channels. The implication in osmosis is water. Specific water channels, pores or aquaporins, AQPs, this author calls them. So, and again, when water or whatever solvent, but we're typically referring to water. And they show you all of these things and then measuring the particles that are there. And so you can see an equilibrium being created. And this is just the idea that they always use this. Here you have a large gate, so the water doesn't have to move, the particles move to balance it out. Versus when you have only have aquaporins, the water has to move. And so to balance out the high concentration of solute, the water moves and adjusts. That's the principle of if you used an osmometer or one of those, like most of the time you probably do that intro bio or high school, things like that. This is super important. Okay, and I'll leave you with this. Hydrostatic force of water. For you and I, blood pressure is hydrostatic pressure. Pushing, it could be on a cell, or in this case, in a blood vessel. That's what your blood pressure is, the force of the water. Okay, whether you want to call it increases for a variety of things. Osmotic pressure, so it's pushing the water in the cell or in the tube out against the walls. And if there's openings, water will extrude like it does in a capillary. Osmotic pressure is the opposite. It pulls it in. It's based normally on proteins. Proteins and liquids create a colloid. So you hear the term colloid osmotic pressure. It's like milk. It's a colloid, among other things. When milk denatures, milk spoils, you get the big clumps, the curds, and the liquid, the whey. You remember Muffet, Tuffet, Spider beside her. So when you make cheese, you take the curds, because you intentionally make curds and whey, and you pack them together in a form, hence the name formaggio. You didn't see? A little bit of cooking skills. So that's all of it. So hydrostatic and osmotic pressure, it doesn't move. Plant cells don't have to deal with that. They have a cell wall. We don't. Animal cells will burst. And so, it depends. So those volumes are very significant. We don't have a cell wall, nor do we have that vesicle that pumps out stuff. And we'll get back to the tonicity after that without short shift. Goodbye. Interestingly, I did miss you.